The ellipse, my ode to the oval. Wait, that's not an ellipse. Well, technically speaking, it is, but this is more of the thing I want to talk about. Let's dive in and find an equation for the ellipse, and a way to describe different shaped ellipses, and an equation for area and perimeter, because we know those for a circle, right? Pi r squared and 2 pi r. But what would those equations be for an ellipse? There's our circle, a set of points in equal distance r from the center. And there's the equation, which makes Pythagoras happy. There it is rearranged. There it is for an ellipse. We'll always use A for the long side. Call A the semi-major axis. This is called a focus, or two foci. Looking at the list, we've got an equation, and the position of the focus will help us describe the shape. Oh, and there's something else about the focus. You know that pins and rope thing, tracing it out. Why does that work? Does it work? We'll put that on the list. Prove the rope thing. Okay, getting to work with coordinates for the focus and a key definition. Eccentricity, the ratio of the thing to the other thing, of the semi-major axis to C. This ellipse has an eccentricity of 0.8. Others don't. A circle has an eccentricity of 0. Because C is 0, and that would mean that the two foci are on top of each other, so they're just, okay, that makes sense. And the eccentricity has to be less than 1, otherwise it's no longer an ellipse. Great! Eccentricity describes the shape. Now, let's take another look at the rope thing. We're not proving it yet, but pull the pencil to there. Distance to one focus, distance to the other focus, the length of the rope. Watch this. 2A is the rope. 2C, that's the distance between the nails, and this is a new definition for eccentricity. Awesome, but unproved for now. We know that the rope thing will give us a cool shape, but will that shape be exactly the same as our formula? We'll find out later. First, put the pencil here. That would make a triangle, our right triangle, which makes Pythagoras happy and useful, and gives us a relationship between A, B, and C. When talking about an ellipse, you could give values for A and B. That gives all the information you need for the size and the shape, but I like to do it differently. Give me values for A and E. A tells you the size, it's kind of like radius. A tells you the size, and E tells you the shape. But we still don't know area or perimeter, and we still got to prove the rope thing. First, though, let's get our radial equation, which means forgetting these values. A new coordinate axis at the focus, and that's not all there is. The sun and the earth, its elliptical orbit, that's Kepler's first law. But my motivation for this video came from Kepler's third law, which involves the semi-major axis A of the planet's orbit. Kepler found that the orbital period squared is proportional to A cubed. Newton proved this was true with his law of universal gravitation, and there's another video on this channel about that, so what's the problem? Well, here's the problem. It's in my astronomy textbook. It talks about the, quote, average distance to the sun. Now, it's not obvious to me that A is equal to the average distance between the planet and the sun. We'll put this on our list of things to prove, that the semi-major axis equals the average distance to the focus from the ellipse. And fun fact, we've already kind of shown this. If we can prove the rope thing works, then the rope has a length of 2A, and that means that the average distance from the foci, the two foci, is always A. Well, think about that one for a second. Because we're moving on to the full radial equation. R is the distance to the planet or the ellipse, and that distance changes. The angle theta also changes. To find an equation for R, we'll look to the distance to this line, called the directrix. And we'll use a new equation for eccentricity. Now it's the ratio of the distance from the point to the focus to the perpendicular distance from that point to the directrix. Huh? Well, that's definitely going on the list of things we need to prove. But let's think about it. First, you're getting closer to the focus, and the distance to the directrix is also shrinking, so the ratio stays the same, I guess. And this will bring us to the end of the list, connecting the ellipse with other conic sections, like the parabola. Same equation here, but here the eccentricity equals 1. Or the hyperbola, where the ratio is greater than 1. Conic sections, different eccentricities, but the same weird equation. A weird equation with that directrix. Wait a minute. The circle, you said the circle has an eccentricity of 0. Oh, how is that going to work? Oh, I see, the directrix would be infinitely far away. If you say so, but where is my radial equation? And can we prove that this directrix thing really is an ellipse? All right, here's the plan. We're going to start with that new definition for eccentricity, then we're going to use that to find a radial equation, and then we're going to show that the radial equation really is an ellipse. Let's go. A new letter, D, the perpendicular distance to the focus. But why the prime? Well, that's why. The new coordinate system gets the prime. That's the relationship. But this is what we want, the perpendicular distance from the point to the directrix. With that, and the definition of eccentricity, the radial equation is within reach. It's definitely an equation, but is this an ellipse? That's what we're going to try to show with this substitution. Great! But again, why the prime? Oh yeah, x prime is the horizontal distance to the focus, and this is x. We'll see him again later. Now, here, what's missing? This is called completing the square, adding something convenient to both sides, and we can do this and simplify the expression down. Yuck. I hope this is worth it. Done. Done? Really? Yes, because this is equal to that if a squared and b squared are the following. And there's more. A, B, C is a times E, C. There. We remember that that's x. And we're done. Radial equation acquired. But the directrix, I'm still not quite clear on that. Where does it go? Put these in the corner. Rewrite A, rewrite C, and get an equation to rewrite D. Wait, doesn't that make D the inverse of C? The radial equation can be rewritten without the directrix. To review, A, B, C, D, E is everywhere. And now we prove the rope thing with a point and lengths 1 and 2 adding to 2a. Go a little bit nuts with the algebra till we get here, which is a nice spot to do some substitution with our old triangle friend. Wait, no, you can't do that. No, you can't do that. That triangle, you're a liar. Because that's circular reasoning. You're trying to use that triangle to prove the rope thing. But you already assumed the rope thing to write out that triangle. You assumed 2a for the rope in order to write that triangle. You're a liar, and you thought you could get away with it. Get out of here. Send in the clowns. No assumption was needed for these guys, and they tell us it checks out. So this is true, and we can continue, or rather finish, the proof. The rope thing really is an ellipse. Done. And the astronomy textbook was right in claiming that the semi-major axis A equals the average distance from the focus, the area of the perimeter. That's all that's left to do, and we're going to do them in part 2. Now wait a minute, hold on. Well, I thought the video was over, but we've been getting some complaints from the astronomers. They're complaining about all these equations for eccentricity. Now, how is an astronomer supposed to use any of these? All right, we'll make room for one more equation for eccentricity, and we'll have to show that it really is what the others are. Starting with the radial coordinates, the sun at one focus, and a measurable maximum, the biggest distance that the planet gets from the sun, call that the aphelion. Also a measurable perihelion, the smallest distance the planet gets from the sun. Eccentricity, so we claim, is equal to the difference divided by the sum of those two distances. Looking at some of the facts we know about ellipses, we can write out an equation for the maximum distance, that's a plus c. The minimum distance from the focus would be a minus c. This is familiar to us from that rope thing. Now all we need to do is plug these values into our eccentricity equation, and we'll show that the new eccentricity equation is the same as another eccentricity equation, so they are the same, and we are happy. And the astronomers are very happy, because we look at this and notice that it gives us 2a, and we remember what a is. A is the average distance from the planet to the star. Astronomers have nothing to complain about, because all you need to do is measure r min and r max, and the ellipse will tell you the rest of what you want to know about that orbit.